Welcome to the second part of system inertia requirements with increasing RE and HVDC in feed, and I'm Carl. In Hong Kong, we have got our generator A and B constructed in 1980s and generator C constructed in 1996. And the generators A and B are actually getting older and older, and they will have more maintenance problem, and they cannot get into their full loads. It means that generators must be commissioned and will introduce more on-time flow. It also means that we have got less rotational energy from local generations. It's very important to be local because just imagine you have got generators and you need to transmit it through a long tie line to the load. In one day you may have got a fault, and that fault will trip the line, and all the generated power will go through another line to the load, and that line will get thermal overloaded. Just because of that thermal overloaded, the line will be tripped as well. And there will be a full segregation between the generator and load, just like the generators in mainland China will stay in mainland China, and they will not transmit their generator power through the tie line to Hong Kong anymore, and the load will just have no power. You may say, okay, we have got generators in Hong Kong, so part of the energies will get sustained, but just because of the discrepancy between generators and load, we have got more load than generator, then the frequency will drop, and in the end the generator will also chip. So as you can imagine, after decommissioning some of the old generators, we have got reduced inertia, and just because of with less excitation capabilities of each generators, we have less voltage control capability. And of course, one generator means one part of the fault current, and also how the system can react to any disturbance. Then it's better to have more and more generators staying in grid, just like getting their minimum load. It is good to have it, but the problem is that we try not to do this because it is not economically optimal. So it also reduces the power availability roll off, and also all these kind of related frequency reserves. Just imagine there will be a disturbance. We want to reduce, of course, the roll off, the frequency nadir. How? We could provide them with some kind of inertia from the rotational energies of local generations. We can have some kind of IBR fault rifle capability, which is to drain out the energies from the DC capacitors in the IBR, the inverter actually. So we want to control all these kind of things, but the problem is that it's actually very difficult because, for example, we want to trigger the under frequency load setting, just because we have getting more loads than the generations, the frequency will drops. But at first, we need to measure the frequency first. It means that we need to have some kind of time window to sample the frequency. And normally, for example, in 50 Hz grid, we need to have about 1.25 cycles, or some better algorithms we can have one cycle delay. to sample the frequency, which is 20 milliseconds. But if we want to measure the FDT, we at least need to have 4 cycles for the FDT. And also we may need to have some kind of intentional delay because we want to measure just like the frequency nadir. We need to wait until the frequency drops to the bottom. Then it will be a bigger problem, right? And also we may need to have some kind of delay on the CB opening time, just like if it is hydraulic, then it will be like 80 milliseconds. If it is pneumatic, which is driven by air pump, then it is about 50 or like 40. Or you may have a CB driven by spring, then it is 30 milliseconds. Then you need to have some kind of delays. But the problem is that just like South Australia, they do the demonstrations on tripping or and arresting frequency drop with the under frequency load shedding, and they discovered that they cannot rescue if the system frequency drops so fast. Just like the one with 6 Hz per second roll off. It's actually not the case in Hong Kong, but we'll have more and more this case because we embrace time flow, we embrace the use of renewable energies or HVDCs, and as all these kind of things like HVDCs are getting less and less on the local generations, and that's why we need to emphasize the term local generations, because it all depends on how much energy that you could rescue your grid during any disturbance. So another challenge with increasing ROE, it lies on protections. Actually, it depends on what kind of ROE that you would like to use. In general, they could not provide negative sequence fault current. It's actually a very big problem, because if you have got a three-phase fault, then it's no problem, because all the fault current will be positive sequence. But if you are getting single phase to ground fault, phase to phase faults, and if you could remember, you are actually getting a network like this, and also a network like this. Which is this is for single line to ground, and this is face to face fault. We need negative sequence to know that it is a single phase to ground fault, it is line to line fault. In most of the protection operations, we assume that there is negative sequence and they behave well as what we want it to be. Then we try to use this to identify if it is single phase to ground fault or is it line to line fault. We try to do this fault type identification and also the phase identification, just based on the negative sequence current. And sometimes we may use it to determine or provide a faster tripping on the single line to earth fault, just because we may not trust the rest on the residue current, which is the zero sequence current, much, and we try to use it. So as you could expect, it affects the accuracies on the directional OC on the negative sequence for the generator protections or the phase detections or any unbalanced fault detections. And also, you may say, can we have the IBR that can provide the negative sequence fault current as expected? So it becomes another problem. Just imagine if the generator or the IBR knows if it is under what kind of fault. And also just like the Type 3 TG, the wind turbine generations, which is based on the DFIG, you can remember that on the status side is direct on the grid, direct online, but on the rotor side we have got converter connect it to the grid. So the parts that we could control is the parts with IBR when we try to control the field and also the voltage in order to give the response on or the accurate sleep on the data such that you can generate what you want to. But it is all about the IBR, the inverter characteristics, and also the machine characteristics. So you cannot fully control, or you don't have the full controllability on the response, especially on the negative sequence. And there is some reports on the phase angle jump PAJ problem on the negative sequence. And for the type 4, which is the PMSG, or we have got a full rated converter in between the generator and also the load. The negative sequence current may be suppressed, and that's why Germany in 2018 they updated their requirements on the inverter-based converters or inverter-based resources that they need to provide enough negative sequence current, or they need to provide the controllability of negative sequence currents for that fault current mimicking, or to provide the detection capability for the protections. Okay, so for lower fault current, you may have the risk of miscoordinations because actually you don't know which side is generated from, and you may have more generations from the main grid and more generations from the generator you don't know, and that's why you can call both of them a source and you don't know where it should be tripped. And there could be a problem of transient instability just because you have got a weak network. You may have distant protections, but actually with distant protections you may have the reliability problems because there is a short line, and it means that for IBR you have got a long source impedance, while for the main grid you may have a smaller one. And actually if design is stripped and you need to use a distance here, the VF here, or maybe under the fault over there, actually is not accurate because it's very small and the noise there could be very large, which means that the impedance accuracy will be reduced and it lengthens trip time, and you don't know where the fault is. Another one is you may have a faster swing, just like here. Originally you're actually operating in the point here, which is the low point. Here is the origin, and this is the low. And normally over power swing, it swing in that way. And we try to set two boundary. Like here we have got the inner, we call it zone 6 and it is zone 7. In most of the protection devices or distant devices, we try to calculate the DC-dt. If it is larger than the set DC-dt, it is a fault. If it is not, then it is a swing. And some of them, they may try to have a timer over here. It means that if we have our points going to zone 7, it starts a timer, and after the timer expires, the points still stay between zone 6 and zone 7 and don't get into zone 6. Then it is a swing because it gets lower and the CDT actually smaller than the set CDT, and it is a swing. So for the operations of power swing blocking or out of step tripping, it's all about the to distinguish fault and swing. But the operations of out of step tripping is about to determine stable swing, which is going in these directions, or unstable swing. Unstable swing, then you need to trip. So for distance, we often call it out of step blocking or power swing blocking. And for timeline protections, we use RX diagram for the out of step tripping. And as you could expect, reduced inertia means that the system actually reacts faster than before, and the swing go faster. It means that if you use a timer, you need to reduce the time setting. If you use the DCDT, you need to change the DCDT set to a larger one, which means that it gets harder for you to distinguish faults and also disturbance. Another challenges for increasing RE is anti-islanding protections. Actually, anti-islandings nowadays, we try to have what we call the voltage vector shift, which is actually, you can see that there could be shift U delta U, and now do you shift, there is a time delay over there, and by this you detect an anti-islanding, or you detect an island. Another method is roll off. It means that we try to have over voltage, under voltage, or over frequency, under frequency, or all these kind of frequency reserve parameters to detect the anti-islanding protections. But at first, it may not be detected within the time frame what you need to detect, segregate or not. And actually, if you read the standard on IEEE standard 2800-2022, which is released in this year's, it says that you have got all these kind of diagram and the zones that you need to stay stable, and out of the zones, just like in the voltage one, you stay stable here, and in that region you can determine if you want to trip or you still stable, or what we call the rise through. Then you have got two regions at least. But for a longer time, actually you may go to the region that you need to determine, which means that you may need to have a faster response. But the problem is that detections of all these kind of parameters needs time. And of course, you may have other methods, just like the active method, the communication method. But all the IEEE standard suggests is try to use communication instead. What do we mean by anti-islanding? We have got a line tripped. For example, you may be tripped by out of step tripping. Then you drive a signal. You send a signal to the other side. Ask for direct transfer trip, what we call DDT. Then you perform the functions of anti-islanding. For the roll call requirement, they have designed two category 2 and category 3, but in IEEE standard, again it is 2H00. For the roll call larger than 5 Hz, you determine if it is chip or a rifle. If it's smaller, please stay stable. So here comes some kind of experience, international experience with reduced inertia, just faced by all these utilities. Actually, they need to determine the minimum inertia requirements for the system. If it is not fulfilled, you need to connect with it with more generators, especially on local generators, or you may have the synchronous condenser. One thing to be noted is that the IEEE standard says that sync condenser is not a mature technologies. Actually, synchronous condenser exists more than a decade, but the applications actually quite not that mature, or not being applied in many countries. And that's why if you really want to try, then you need to take the risk that you cannot fully control. You don't have the capability to control it. So just like for example, you have got Tasmania, and they have drawn the graph on the roll-off, the inertia requirement, and also the fast frequency response. First, they draw a line on the DFDT, says that okay, you can't go through that line. Then they have determined the inertia available on the blue line. If I say you may have under frequency load setting, as you can expect it, the major problem of under frequency load setting is the detections on under frequency load setting, and it means that if you don't have this kind of delay, then the response is actually immediate. You don't need to wait for the start up of the generators. You don't need to wait for the start of the energy storage. All these kind of things takes time. Then we can shift the inertia requirement upward, so it becomes this line. And for example, we estimate the inertia requirement line with the generator tripping line, then you can see that the inertia required is 3,800. Then it is their way to determine the minimum inertia requirements for the grid. Okay, for the ERCOT, they actually have a graph. It's actually a very important graph on the under frequency load shedding setting to the inertia. For example, if the under frequency load shedding is set on 0.6 seconds, the under frequency load shedding can be provided within 600 milliseconds. It means that you need to have 100 gigawatt second inertia. And for their grid, they have seen their minimum inertia under the operations of under frequency load shedding is at that point. So first, history is important, and second, you need to have this line, and luckily you can see that it's like a parabola. It means that just like you can have the line just like t is equal to alpha I squared plus beta I plus gamma, then you need to find out all these kind of coefficients to plot the line, and you can estimate your inertia requirement based on your under frequency load shedding setting. Now we have got more and more technologies to provide inertia or frequency response. First is about the synchronous generator, just like what I have been mentioned. It's all about how many synchronous generator on bar. If you connect more and more generators on bar, then you will have increased the rotational energy. It's nice. But the problem is that it's all about the economic dispatch problem. You may want more and more generator connectors just because of inertia. Then you need to pay more. But of course you don't want to, and that's why you try to have the optimal one. At first, you need to have enough generator for the optimal one, or else you need to go for the tie line. Then this decision will make your grid highly likely to be unstable. Another consideration is about the capacity curve on the generations. Just like here, you can see there's a stability curve. You can see that the armature heating and field winding heating, or the prime mover limits, the shaft, how much power can generated through the shaft, to going from the mechanical part to the electrical part, going from turbine to the generator. All these kind of constraint, and also there will be a P-min requirement. And all these kind of capacity constraint will make you feel more difficult on the decisions how many generators that can be connected to the bar or connected to the transmission network. Another consideration is you may have motor loads. It's actually good to have motor loads connected on bar, but just think where could be a place that having many generators, many rotating objects to use that rotation energy. Actually, there will be not much, and that's why in UK they have got number like for 36%, but I don't think Hong Kong have that much, because in most of time the rotation machines in Hong Kong are actually connected with the VVF, which is the variable voltage variable frequency drives, and these drives actually separating the loads with the generations or with the transmission network, and this cannot provide any frequency damping uh, as well. And another concern is that okay, you may have all these kind of motor loads, but you don't have that parameters, so that you can't do any planning, or you don't have the capability to do any estimations on how much generator on bar can be reduced just because of the motor load. Another consideration is like synchronous condenser. You can see that there are many companies or utilities that they will try to use the synchronous condenser to increase the fault level and also support the voltage through the excitation. You can see that you can control the reactive power, but actually you need to pay for the investment cost, which means that it's all about money. And second, you can see that it may takes up energy just because of loss. And that's why even you have got a synchronous condenser first, you may hire a consultant or a supplier to build it. But second, as a system control engineer, you need to know the capability and also how to control the synchronous condenser. Is not that easy, and you need to take some time for the training. Of course, you may think of HVDC, you may think of energy storage, and in the end, it's all about the energy in the frequency line, and that energy comes from generator minus load, and also if you have got the inertia, it is good, but in most of time the HVDC and also BESS can help. It's all about how much energy that you can release from the grid. So for the HVDC, you may have emergency power control, but I must emphasize that you don't have any standard nowadays describing or design of advanced control in HVDCs, and you may not have that function. Just like another function is called oscillation damping control. These functions are not even included in the latest IEEE standard, just because of the immaturity of the technology. But anyway, just imagine you have got advanced HVDC link, and it is already the max power that you can provide. Just imagine if you have got another frequency, you need to provide more energy from one way to another way to support the grid, right? So you may ask for emergency power control, which means that overloading the line or the IGBTs in the converters a bit in a short time period to provide more power. Or another way is just share down some of the transmissions to tackle for the overfrequency. As I have said, for most of the frequency events, one part of the transmission network is under overfrequency because they have got more generators than low, then that overfrequency can trip out some of the generators, then it will be all okay. But sometimes you may trip the largest one, and in the end you may have low larger than the generator, and you need to shut down some of the loads, and it's what you don't want. And that's why you need to have HVDC link to shut down some of the tie flow. And on the other hand, you have got a grid that have more loads than generations, then you need to have an HVDC lines to provide them with more power. So that emergency power control can cause capillary overload, but just check if your IGBT could take. It's all about the I square, which is the thermal capability. You may have something like in virtual inertia, inertial emulations control, but it's all about changing the set point of output power to limit the FDT and also delta F. You need to think where the power comes from. To power, you may say, okay, we have got all these kind of submodule capacitor charge, then it's good. But once you drain out, you need to supply it back, and it may impose the stresses on another grid, the supplying grid. Another considerations, another technologies is energy storage, but as you can see, the problem is the response times. Just like this one, you have got frequency. After detection, you start to rise the power, but that power raised to 90% takes times, and this is the response time. And you need to consider response durations. Just like in most of the time, if you want to provide inertia or fast frequency response, the FFR, then you need to have a supercapacitor because it can respond in some cycles, just like 4 to 6 cycles. Then you can push all the power into the grid and rescue the grid or rest the frequency. But it can sustain for seconds, but that's enough because you have all these kind of fast other fast frequency response. You may have under frequency load shedding, you may have primary or secondary frequency response, the PFR or the SFR. This can help. Just sustain it until day comes. But as you can see, the frequency nadir is here, and this cannot rescue or arrest the frequency anymore. So please select something fast enough. Although their response duration may not be long, or their system life may not be long, it all depends on what you need to provide. It should not be ignored or neglected. Of course, you may have other technology, but this is future technologies to provide inertial frequency response. Just like the static smart load, you may heard the term electric spring. It is to control the series voltage before connected to the load, which is a non-critical load. The non-critical load may be voltage dependent or maybe frequency dependent, and you could control the series impedance or series voltage to reduce the load, in short, such that you can do the functions of under frequency load shedding, unlike the one with protections. Just because you have got the IBR, you have got the inverter, you can react much faster. And you need to consider the DF/dt. You may have the DF to control or to provide the preset. With the presets, you can actually to provide the output of voltage and also the phase angle in order to control that VE as the spring voltage and also the phase of the spring. Another method is like the motor load, but you know the motor actually having a load or PM as a function of F and also the FDT. Then if you reduce the F, then you can reduce the PM as well. You have got all these kind of frequency regulation capabilities through the like wind turbine, energy storage, PV, synchronous generator with or without governor. Yes? First, you need to consider the response of the governor. If you could remember, we have got the FP curve here. At first, the primary frequency response is here going up and down to determine the output power of generator. Based on the frequency. And the second part is through the governor you can control the line and hence control the output of the generator. In return, you actually need to control the flow from the steam drum in order to control the mechanical power to push the turbine, and hence you can have a larger power to push the turbine, hence generating more while keeping the frequency at that positions. So all you need to check is about the response speed, just like what I have mentioned. The speed is very important, or else you can't even rescue or arrest the frequency. You may need to consider the response. Why do you need to consider response? Is because just like here, you may have a wind turbine. You can extract the energy from the rotational energy of a turbine, but you need to pay back. When you extract the energy, the frequency drops. How to increase the energy? You either provide energy from the wind, but in short, you don't have a gust. That's the wind could push your generator back to that frequency. Then you need to absorb the energy from the grid to motor back that frequency. Then it could be a problem because you may save the grid with the energy, the rotation energy, or more energy from the generator or the wind turbine. But suddenly you get back that, and you could push the frequency back to a worse position just because of that energy that you obtained from the grid to motor back your wind turbine to that frequency. So shape is also important, and also durations. And all of this is about what kind of response, the frequency response that you want to buy from all parts that connected to the grid, or what you ever have. And it's also about the operation of inverter-based resources. You may have inverter and inverter-based resources, or you may have a synchronous generator. Just like if you are as the transmission network owner, then you have generators. If you have an IPL, then you have an IPL owner. Then you need to consider the frequency control capability, you need to consider overloading capability, and also synchronizing power. For synchronous generator, you have got a rotating mass. There is a strong coupling between the generator and also load, because if the generator is getting slower, it becomes an induction generator and absorbs power from the grid to motor back the frequency. You could do that. And if the generator's frequency drops and you can't rescue it because of you don't have enough frequency reserve, you can't trigger your under frequency load setting, then the whole grid frequency will drop. But if you have got IBL, no matter what happens in the grid, you can still generate in that frequency. You can just blind your eye and keep on generating that frequency. It's all up to the system positions or your decisions. Another concern is overloading capability. The major problem is all these kind of constraints that we can see in the capacity curve that I provided in last pages. But for the IBR capabilities, all about IGBT, which means that, for example, you have got all the shunt path providing all the currents, the full rated currents from the generators to the transmission network. But suddenly some of the IGBTs are burnt. Then you lost some shunt branch and the output rating is actually limited. And during the emergency situations, you can't provide EPC, the emergency power control anymore, just because of that. Then you need to consider it. Another concern is about the frequency control. You have got all these kind of rotating mass, and that rotating mass is a way to provide the frequency control. Once the frequency drops, the rotating mass keep pumping the kinetic energies to the grid such that the grid frequency can sustain. But for the IBR, you can perform any inertia emulations, but you need to think where the energy comes from. You may say, okay, I may have a battery supporting the grid in short, then I can pump the energies from the battery to the grid. Or you may have the HVDCs, then you have got all these kind of submodule capacity and energy, and you can pump back. Or you can perform the EPC, then it's all about where the energy comes from. But for all this kind of IBL, it just changes the set point. If you cannot provide the energy that your set point wants, then you can't provide the energy to the grid anymore. Another terms is what we call the grid forming and also grid following. In short, grid following is that you try to synchronize with the grid, synchronize yourself with the grid, and you try to perform any voltage control by considering how much real power and also reactive power pumped into the grid. While for the grid forming, it's like you are an anti-island, you are an island, and you want to have your frequency and also voltage yourself. Actually, you can couple it to the grid using the grid forming capability. You can just provide the energy based on the frequency in a small island. just that your island is weakly connected to the main grid, and all the power discrepancy is satisfied with the main grid. You can pump or you can release the energy to main grid without weak link, and you can sustain it. You can sustain yourself in an island. Then it's all about the frequency power drop and also voltage relative power drop. Like what we have in the synchronous generator, all this kind of governor and also the AVR. And it is a drop. It's noted that in most of time, especially in DFIG, in most of time, it could have a negative resistance, and that negative resistance, seeing from the state design, can lead to converter instability because it is weaker than the weakest coupling, and it's all about the grid control, the grid coupling, and also the time constant. So as you can see, you have got all these kind of difference in the synchronous generator and also the IBR here in terms of the synchronizing speed, harmonics, coupling impedance, fault level, or oscillation damping, and so you can read it yourself. And for the IBR, you can still have several terms, just like a single converter, which is to mimic the performance of synchronous machines, and through this capability. Then it's all about the calculations and also the control on the output power. You need to set the output power here, and also compare the set point and also the actual frequency to determine how much extra power that you need to pump into the grid. Also, you have got a term called virtual oscillators, which is to mimic the nonlinear behavior of one pole oscillator. It can limit the response for quick transient and also stabilize the system after any transient. But for the converter itself, you may want to have it as a grid forming, which is kind of more advanced. I don't think it is more advanced because we have got all the inverter or converter in the past in the grid. That is grid forming. Especially you need to operate it yourself as an island. Then of course that converter must be grid forming. But under faulty conditions, it may change back to grid following mode because of the restrictions on current. Just like when the voltage drops during disturbance. It seems like you need to push more power with increasing current, but the problem is you can't overload it. And also, under fault, you can't provide a reliable frequency or a sinusoidal waveform to the PLL such that you can output a correct estimated phase angle and also frequency. Then you can't do all these kind of DQ transformations, and hence you can do a good voltage and frequency control, and also the drop as well, using the IDIR. the IQ. Uh, or on the other hand, it is all about the increased in virtual impedance to limit the output. You can have that virtual impedance. You can change the virtual impedance to limit the output. Then you can still stay within the grid forming converter. Then it's all about your control. So here comes the last part, and we try to quantify the frequency reserve. Again, under your frequency disturbance, you need to provide frequency reserve. Then you have got all these kind of frequency products. Then you need to consider volume, how much you procure. Just like here we have got inertia in grid. Then I can be it's enough to have a lot of generators on bar. Then I can reduce the FFR to arrest the frequency until the primary frequency reserve comes. But the problem is the current system configurations, just like the coupling. Yes, the equipment capability, the coupling, the generator profile, how much generation available, like the number of generators on bar, or flow or not. You may have some kind of pre-control on the wind and also generator, just like what we call the power the delta power control. Delta power control to reserve part of the energies to as a spinning reserve. You may have a lot of reserves, and you may have the market and also the customer behavior, just like you suddenly increase the price and the customer they are not to accept it, and they try to shut off all their loads, just like their air conditioners, their TV and so on. And you may have an HVDC link that can borrow energy from, but here is the note. It is unlikely to import large power with low load, because once the HVDC tripped, the whole grid will be blackout. It is no good, and that's why please keep local generation. Like around 60 to 70% of loads, it will be good enough. You can do some kind of load controls, you can do some kind of market response in order to reduce the load. You can have under frequency load setting, but at least your grid is still savable. And also you need to consider the capacity constraint and also the stability constraint, especially on the delay power recovery. You may have a fast controller, but you need to have enough power to restore back to the system. Unlike you have got a synchronous generator, once there is disturbance, then you can just push larger or more steams into steam drums and also turbine to restore the frequency and also restore the energy in the rotating mass. You can't do that in wind turbine. You need to absorb energy from the grid to accelerate, or you need to have more wind or else you just need to wait until the wind turbine goes back to the nominal frequency. And it means that you can't have normal real power output after the frequency response for a while, and you need to have that control. So it's all about the cost modeling. It's all about how much frequency reserve that you want to have and where does the frequency reserve you want to have, and it ends up the concerns about the challenges, the technologies that provided, and also how to quantify the frequency reserve in this part on the system inertia requirements with increasing RE and HVDC infeed. And thank you.